So I plan to have a uh, uh, um, uh, reading session for 40 minutes. Then we might go through the slides and 4 or 5 sections. Then we might go through some exercises, and the next time, since we have 2 slots for this, the next time we might go through some code and complete the rest of the chapter. So uh, let's now. What do you say, guys? Is this format all right, or should we start right now, or do you guys need some time to read?
For me, both options will be okay.
Cool. Uh, Anyone else? Or we might go with the first option here.
I'm fine by starting right away, but if anyone needs reading time, they should probably assign a reading time.
Cool. So let's start then right away, because we have many small things to discuss. Uh, uh, Please raise your voice if you need some reading time too, because we can extend it. Ah, the sessions can be extended by half an hour or so. Uh, cool. So let me now start to share my screen. I hope you guys can see my screen.
We can see it.
Cool. So let's start with the chapter. Running by dynamic programming. So I was thinking of going through the slides a bit too, because these are some of the best material that I could find, and this makes a lot of sense. Uh, First, let us try to go through what dynamic programming is. And David Silver defined is as a sequential or a temporal component to the problem. How do that make sense in the RL context is uh, uh, since we last time looked at the MDPs and how the value and the policy iteration kind of uh, uh, occurs with respect to the Bellman optimality and the Bellman expectations equation. So we will take a look at uh, those perspectives with the RL context, and we will try to get to the bottom of how the state and action spaces are iterated and what and how dynamic programming is the basic component. Uh, the dynamic programming paradigm is the basic principle for our end-to-end, no, end-to-end of how we break down this large problem into a sequence of sub-problems. So, I think so. Everybody is familiar with what dynamic programming is, and okay, then what was the requirements for dynamic programming? Uh, since this is the principle of optimality for optimal substructures, we are trying to uh, 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 get the best uh, or the most approximate uh, 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 how do I say it, the optimal or uh, the equations that we looked at last time. This is the Bellman's optimality equation. So let me try to take it from the top again. These are the requirements, as you can see on the left. Dynamic programming is very general solution method for problems which have two properties: uh, optimal substructures and overlapping subproblems. Here, we have principle of optimality that is applied, and the optimal solutions that can be decomposed into subproblems. Those overlapping subproblems can recur many times, and those solutions can be cached and reused. So these are the overlapping subproblems that we look at. Then we uh, had MDPs, and wow, and how the uh, uh, MDPs solve both the Bellman's and the value function that it stores and reuses the solutions. So that's one thing for uh, why that's one of the properties of why we use MDPs. Then we go on to his viewpoint of planning by dynamic programming of how it's done here. So this assumes the full knowledge of MDP, and uh, for prediction, we have state action in environment dynamics, then reward, and the discount factor. These are the five parameters with the policy pi for Markov reward processes. We have these four guys here, and the output is the value function vpi. So this is for prediction, and for control we have these uh, inputs, the outputs, and the optimal policy. So these are the two things that we take a look at. uh, and on the text you can see this line here, and this I have highlighted. Try to zoom in. The key idea of DP and of reinforcement learning generally is the use of value functions to organize and structure the search for good policies. So that's what we are doing here. Uh, here S and the other thing is we have assumed that the environment is a finite MDP and the state of the SAR, as I've just alluded to, with the set of probabilities with this, that reward R with the S plus is the terminal state if the problem is episodic. Uh, S plus the terminal state if the problem is episodic. So that's the notation that we use. And then they have talked about the approximations too. For the task with the continuous state and actions to quantize the state and action spaces, then apply the finite state DP method. This is for the limited time interval if we are iterating through all the states. So, how do we constrain our policies with respect to the time interval that we have? The inner loop that we are trying to iterate upon.
Excuse me, regarding this point, I didn't fully understand what it's mean that in a continuous, for continuous tasks, actions
Okay.
can be quantized.
Uh,
Could you
yeah,
an
maybe
explanation? Thanks.
the S plus.
No, I mean, it's written there a common way of obtaining approximate solutions for tasks with continuous states and action is to quantize the state and action spaces. What is meant by that? What will be the solution for continuous states?
Now, for the continuous states, we had the problem of looking at it from, I think, the control perspective. This guy here, or I might be missing something, but for the continuous way, uh, it's kind of like uh, the implementation perspective. If we look at from the empirical point of view, those continuous states and actions have to be uh, uh, managed in some sort of bins to then iterate over some sort of divergence. If I am looking at it from a implementational point of view, but I think so. I'm missing the point here.
I mean, I just marked, and it's written afterwards. These methods we will be exploring part 2. That's why I didn't, pay much attention to the last sentence that I didn't fully understand. I just thought maybe you had an easier way to have a better interpretation of that. But if not, it's not the case. Don't worry, we will face it in part 2 of the book.
Yep.
Yeah, I guess that like simple interpretation here is that if you look at the formulas, we are summing here over the states, and in continuous case we cannot sum over the states because those are continuous, right? And the authors mentioned that like a simple way to treat this would be quantize the states. So in this case, we, instead of dealing with continuous state space, say for example, for like for a car, a state space is continuous because we have like a continuous number for, say, latitude and longitude, and for like the angle, directional angle or something like that. But we can represent that as like finite number of discrete states if we quantize it with some granularity. So basically what it means to directly apply these formulas to the continuous problem defined in continuous domain, you need to like convert it into a discrete problem by quantization. So that nothing like
Okay.
complicated.
Now I think I got it. Okay. Just we have to discretize it. Thanks.
So this was the idea of DP to organize the structure and search for good policies. And we can easily obtain the optimal policies we have found in the optimal value function, that is the V star or the Q star, which satisfy the optimality equations. And these are the 4.1 and the 4.2 are the equations that we looked at. And we will apply our TP algorithms into by turning them into one of our assignments. And uh, the two kinds of formulations that we will look at. So this is what this text means. I think so. Everybody is familiar with these equations. These is the max. It's a kind of a optimality with respect to the greedy, uh, and this is the state action. This is the value action. This is the state action. Yeah, I might be confusing the terms here, but yeah. Uh, then let's take uh, peek at predictions. This is the iterative policy evaluation, which is there. They have David has defined it in iterative application of the expectation of Bellman's equation. So this is with respect to uh, expectation application here, the expectation application. And this is a simple way to evaluate it using synchronous backups. What they do is for all the values at this time step, let me try to uh, zoom. Can you guys hear me?
Yes, we can hear you.
Okay. I thought my Zoom has crashed or something like that. No issue. I hope that I'm unable to draw right now. I think so. There is some settings that I need to look at. I was thinking of making some sort of no issues. So what we can do
Excuse
is we can, yeah.
Uh, I would like to share you my understanding, a general perspective
Yep.
about this. To put it into context, as I understood it, so this dynamic programming. So I was watching the other lectures, also from DeepMind, the newer ones
Mm-hmm.
of 2018,
Mm-hmm.
and there was a slide explaining there are two fundamental problems in reinforcement learning. The one
Mm-hmm.
is learning, and the other one is planning.
Mm-hmm.
And there was written there, for learning, the environment is initially unknown. You don't know it; it's unknown, and then the agent needs to interact with the environment.
Mm-hmm.
Whereas in the planning, you have a model of the environment; it's given. So, and in this case, you don't need to do sampling. You don't need to interact directly with the environment.
Mm-hmm.
Uh, so one of these methods, or well, these methods are called dynamic programming, which is this
Mm-hmm.
one. So basically, the definition is, in these cases, we have a model is
Mm-hmm.
given, and then the most ideal scenario will be where you have full knowledge or access. You have a perfect model of the environment, which is also written here in the book. So
Mm-hmm.
this will be the simplest case. In practice, it's not always like that, that we have a perfect model of the environment, and that will be just most of the cases, and those will be the methods that we will study later in the book. In this case,
Mm-hmm.
dynamic programming is where we have the perfect model, and in this case, uh, Markov decision
Yep.
process.
Mm-hmm.
So basically, the key word for me was planning and a
Mm-hmm.
model environment. Um,
Yep.
yeah,
Yep, yep.
that's
I totally agree. With respect to dynamic programming, there are other ways to solve. This is just one application of in RL. There are so many ways, which I think so. We can find books on it. And how do we properly solve it? But with respect to the MDPs that we currently are totally in, with respect to the planning, as you have just alluded to, we have, uh, yeah, uh, uh, how do I say it? Uh, we turn the Bellman equations into these assignments. So, yeah. Uh, Other than this, yeah, please feel free to jump in if you guys have any additions to it. And yeah, that is my point of view.
that's it. And the last thing that I would like to share is that in the previous chapter we were only framing the problem of reinforcement learning, just defining the concepts, and this is the first chapter in which we learn methods for
Mhm.
solving or applying the Bellman equation and solving the problem, find the real optimal value states.
Cool.
That's it. Thanks.
So, as we can see, they have defined here. But let's go through the text first. Then we might look at the backup diagram here. How is it performing, or what does it mean here? So, yeah, in the policy evaluation, this is the prediction problem that we are looking at. Then this is the defined as the expectation of the policy over these guys. The return conditioned on the state space, which can be expanded as this, have, which can be written as the discounted product of the value of the policy here. So yep, this is from 3.9. We have expanded it further, and it can be written in the end as this guy. So this is just the expansion, and we have the notations here. And the expectations are subscribed by pi to indicate that they are conditioned on pi being followed. The existence and the uniqueness is long. This is the discount factor gamma, which is less than 1, and eventual termination is guaranteed from all states under the policy pi. And this is the environment dynamics that are known as the S simultaneous linear equations. The where it's unknown and the v pi is given as S, which the v pi of S belongs to this the state space. This is straightforward, and we have looked at it in the last chapter too. But here, the initial approximation, if I can show you the. So here, if this is the example which they are referring to, here the initial approximation of the 0th uh, uh, is chosen as a sequence of zeros. So this is what the VK is, which is totally referred to as, I think so here it's referred to as, yep, these guys, the approximate value functions. Then the each successive approximations is obtained via the Bellman equations that we have just given for pi. This is how it's defined as, and this is the fixed update rule that we get here, and because of the equalities in this case. Yeah, then the sequence can also be shown in general to converge, as they have written. This is known as iterative policy evaluations. So yeah, this is what David Silver has given in his talk too, of how they have reached this. What were the iterative policy evaluation steps that they followed? Mm, and then we look at the successive approximations, and this guy. We looked at the expected updates as they have defined in the text here. Uh, uh, this is with respect to the one-step transitions that are possible. So we can see this, we can visualize this from this perspective on the slide here. So the successive approximations from VK plus 1 from VK, we can visualize it like this. So this is the root, you can say, the action that we take, and the reward probabilities. Then this is the next state that we obtain. So this is kind of a, and then we take the expectations over this and kind of uh, uh, evaluate or approximate based on the conditions that we have, which is these two equations. It's the same as this. So yeah, it's just a bit of notations that is different, but yeah, this is the same. And this is the visual form of the Bellman, sorry, the backup diagram of this. This is the backup diagram that was introduced in chapter 3. Yep. So, any queries? Cool. So, let's move forward. So this is with this paragraph defines uh, 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 implementational approach of how do we try to implement it, and that depends upon the order in which the states are. So this is a whole sweep through the state space, to the state space that we do in order to uh, uh, iterate through the states to uh, ensure some kind of a coverage that we have uh, in the end. So this is uh, with respect to the convergence that we want to reach to. So they have defined it here, and this is the example. I think so. We will take a look at it in the text in the next page. The complete in-place version of the iterative policy is shown in the pseudocode. Yeah, so this is the pseudocode. Firstly, we assign all the initial state space to 0, and then we iterate through it, give the maximum of this guy or this guy, v minus v of s. That's the values that we have got. So you can see from here that bk for the random policy. This is the example. In the next space we have this, and for k equals 2 we have this. So it's totally dependent upon this equation, the iterations that we do.
Yeah. Regarding this example, I have a following question. So in the example, he says like if we run out of cars in some in one of the places, Jack is out of business. But later he says that we treat this as continual task, and like
Jack's problem,
yeah. So about the Jack's problem.
the Jack's rental problem. Okay.
Yeah.
Uh-huh.
Yeah, so here he says that that if he's out of cars at that location, then business is lost. All right, so that sounds like an end of the I don't know, trial, right? And here he says we will formulate it as continual finite MDP, or continuing. But like, is it really necessary to formulate it as continual problem if we have like this clear termination condition? So that's kind of, and that's one question. And another question, like how do we proceed when we enter this terminal condition, and basically just like continuing doesn't make sense from that point, right? Because we don't do anything. We are out of business, right?
Yep. At that point, it doesn't make any sense because if the uh, if the
So we will just treat it like zero reward for eternity, right? Just like that, as we discussed in the previous one of the previous sessions when we reformulate the like episodic task as a continuous task. We treat this terminal state as infinite. So
Yeah.
would it be like that? So we do not restart, like say for example in this pole balancing problem, we can kind of treat it as continuing problem and restart every time, like every time we fail. But would we restart here, or does it matter? Maybe we can just do it the same way as in that pole balancing problem. But I don't know, just it doesn't sound good from like real world point of view. Like if you're out of business, you will not just start again with the same business again. So we do it like, I don't know, it just kind of a bit confusing, this like collision of continuing and episodic tasks in this case.
Yep. Uh, totally agree to. But this is treated as a continuous problem because uh, 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 those cars, if we look at the environment dynamics, then they need to be at some location at any point of time. So those cars cannot uh, uh, be kind of like if or we they haven't considered the case in which those all the cars are in transit, or uh, 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 if it's currently being moved for I think 2 or 3 days, and in that particular time, if someone tries to uh, 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 how do I say it, book a car, then they won't be able to get it. But it it is not out of business in that sense. So yeah, that is one case that they have to consider from a real point scenario, but the assumptions are uh, kind of totally limited or narrow here. So uh, as they say, Jack can move them between two locations overnight, and this is the $2 per car moved. So that's the constraint that they have put in. Uh, but yeah, I agree with your viewpoint, but it's like there will be some sort of uh, 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 I don't know, some sort of uh, transitions or I'm totally because the availability and the if we consider the discount rate too, if we are expanding our state space, then uh, with respect to the policy iterations, uh, mm, I do not know.
Hi, to Arthur's question, the first one, my interpretation is that business is lost means only there's no reward. I mean, the
Hmm.
customer cannot get the car, so you don't get the reward. Uh, and to the second point, the continuing task is, yes, it's a business and it keeps running day after day. It's not like a game where you have a finish state and then
Hmm.
you repeat it again. So it's just,
Yeah, but the author says kind of explicitly that that if Jax runs out of cars at a certain location, then the business is lost. So that was kind of from my point of view, it would make more sense if you got no cars, you get no reward, but that doesn't mean you like out of business. But just that particular sentence was kind of confusing for me. But yeah, I will try that in code and see what particular setup matches their results. And I
Hmm.
think then I would maybe at least understand what they meant. But yeah, so 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 it's from my side, it's not like question, but I was just curious if that's confusing only for me, or that's kind of
Hmm.
everyone have some kind of fuzzy uh, understanding of this formulation.
Yep, and plus here too, if we take a look here, the here on the y-axis, it's from 420 to 612. Uh, I do not know how this comes into play with respect to the uh, iteration that uh, is being done. So I have a query here. Uh, and this is the cars at the first location, cars at the second location. Uh, the from if they move from 0 to 20 and 0 to 20, then what's the rate here like? The value iteration of how they do it. This is the kind of a projection which I'm unfamiliar with. I had a query here. If you guys have some viewpoint of how this is formulated.
So this projection, like basically, we have kind of states, and yeah, for me it would be like easier to imagine this as a heat map. You know, when you have like basically it's very similar to the grid world problem. We have like 20 by 20 possible states, right?
Mm-hmm.
When we have like 0 cars to 20 cars, and for each state we like each state like corresponds to how many cars we have in two locations, right? And
Mm-hmm.
if we move to like in this case we have this very simple problem when we have only two like spots, but you can kind of extend it into like n spots for car rent, and then you would have like this multi-dimensional state, right? But in any way, like for to each state certain value corresponds, and you see that obviously when both spots are full, like 20 cars in point 8 and like in location A and location B, we have the highest expectation because we always can like satisfy the demand. But well, like if we don't have any cars, probably we are we have lower expectation. But I guess that kind of answers my question that in this case we don't really stop, but we wait until our cars come back, right? Because this expectation is 420, and yeah, it's quite higher than 0.
Mm-hmm. Yep, yep. That that makes sense.
So and these diagrams for policy basically depict the like decision boundaries, right?
Mm-hmm.
So here for each boundary we
Yeah.
take certain action. So that those are decision boundaries, and obviously as we are expected to lose cars at like at one location and like stay constant on the other location because of those how those lambdas for distributions are defined. Then we so we have this like basically asymmetrical policies. Most of the time, like we are moving the cars from one location to another more often.
Mm-hmm. And plus the locations with respect to the cars, they kind of defined as this it as some kind of little Gaussians too. But yeah, they have taken here uh, uh, this first location and the second location. So okay, if we had multiple locations, and I was thinking how could they have projected it here uh, for the two locations that this kind of a diagram makes sense. But yeah, uh, for uh, if we try to uh, scale it up, then uh, some kind of MDN based Gaussian projections might make more sense here. Yeah, so that was okay. So we looked at this problem and I discussed this. Now, let's quickly since yeah. Do you guys have any queries over this diagram? This the policy improvement, or the example 4.1. Any comments here? Because this we looked at last time too, with respect to the baby robot example and the other examples that we had uh, of how those transitions, those value functions, and uh, how the random policy, the greedy policy was being uh, ev- uh, evaluated. So, do you guys have any comments, any suggestions, or any queries here? Cool. So we will, and these three exercises are easy too. We just have in the 4.1. This is the policy, the queue action pair of 7 down and the 11 down. What will be the values here? In the 4.2, they have asked about uh, 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 VPI of this state, a new state that is being added just below it, and what's the transition probabilities that it takes, and the dynamics that the new agent of sorry the of the mm, new state here, and what will be the policy in this case. So this is simple too. It's just the extension of the above equations that we have looked at. Or you can see here in the slides too, and you will get the answer with respect to the policies that they have changed. So now let's take a quick look at the policy improvements. Yeah, so this was the convergence of the small grid world. So you can see at k equals 3, the optimal policy is reached, and you do not have to go to k equals 10 to, but the values are being iterated. Uh,
I have there's a question for you regarding exercise 4.2.
4.2, okay.
Exactly. Regarding this new state 15, I think in both cases you have an equal or very similar state value in state 15 than in state 12.
What if you have equiprobable values in state 15 and state 12?
Yes, that's what I got. I don't know if you got the same.
Uh,
That's my question to you.
uh, Values for state 12, 13, 14, and 15. State 12 and state 12 is this guy, right? So if we try state 13 here, 15 is there. Why? Why did okay. Choose, can you see my mouse pointer?
Yes.
Yep.
Okay. That is specifically. I'm trying to draw. My Zoom is currently stuck. Recently changed my base OS, and I'm taking meetings from Ubuntu. It has stopped responding. Uh, 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 anyways, I will do a simple analysis, and maybe I will report the uh, results after the call in the Slack. So, yep. Or
Okay.
if someone else has an answer right now, if they have worked on it.
Well, I don't have like clear answer, but we can speculate on it. So the first part is what if okay, so the actions take this agent from state 15 to we treat it like if it were like for actions left and right, if it were like 13, and for equiprobable policy we would take a quarter of obviously for all actions we have reward -1, right? And the sum of the next states would be quarter of -22, right? Plus quarter of -20, plus quarter of -14, plus like quarter of its value itself, right? So it's kind of recursively defined in terms of itself, and that would be so that would be like you kind of can calculate it by plugging in this into a formula, right? And the same analysis may be applied to other states. So you just take the reward you get, which is -1 for every possible action from state 15, right? And then you sum over all the next reward or next states values multiplied by the probability, and that will that will just add another equation into our system of equations if we solve it like kind of like I showed in the previous session by solving the system of linear equation, or if you treat it as like iterative process, then you would just kind of do the similar kind of updates to this state 15, but again it is just defined in terms of state 12, 13, and 14 and itself, and this is determined by this transition probability. So in the first case we have transition probabilities of 25% to state 12, 13, 14, and 15, and the values of other states wouldn't be changed because we cannot get into the state 15 from those states, right? Because of that, the value of state 15 is not incorporated into the values of any other state. Okay, does it make sense? But if we change the transition probability of state 13, in that case, the value for state 13 itself will change. And because the state 15 is further away from the terminal state, the value of state 13 will drop. So it will become lower. Okay, and what is the last yeah, so and for the last one, what is value of equiprobable random policy? So it would be all the actions take it yeah, it will just again incorporate the new value for state 13, which takes into account the value of state 15, right? So that's how it dynamics change.
Yeah, no, I totally agree. This will give a formulation with respect to the transitions that we have. But yeah, I agree that from 15, that will be just the action of going north, and the value of 13 will drop too. Then I think so that state will be a kind of a limbo state in which it's the our agent is stuck. But uh, and if we compare the probabilities, it will be quite low, uh, uh, because it's not adding up to reach anywhere to. So from an intuitive perspective, what does the numbers signify? So yeah, yeah, totally right on this one. Uh, And then for the exercise 4.3, we just had to convert it to action value instead of the state values, the 4.1, 2, and 3 that we had. Cool. So now let's move ahead to the policy improvement theorem. How did they? So this is what we define in the policy improvement space. So let's take this example first. This is the starting space in which we have defined it as all the state space spaces are defined as zeros. Then the upper arrow here you can see is the evaluation phase, and the lower arrow here after a value has been selected is the greedy phase here. So these are being kind of swapped one after the other. So this is our life cycle here inside that loop. So then it goes and evaluates it, and then improves it based on the greedy policy that we have, and until it reaches a optimal pi and v. So these are the two policy evaluation and the improvement steps that we can see from this. Uh, uh, this is the proof of the policy improvement theorem, of how it converges to this guy here. Mm, and these are the pairs of deterministic policies and this guy. Yep. The next iteration prime must be as good or better than this. So yep, these are the straightforward formulations that help us reach to this point. So, this is the new greedy selection step, as we have defined here in the equation 4.9. These are the conditions on which it is defined. And, yeah. This is, I think so, based on the stochastic nature of the uh, evaluation and improvement case. I think so. They have written it somewhere. Yeah. Yeah. This is the okay. This is in a specific condition. In addition, if there are ties in the policy improvement step, such as 4.9 equation, that is, if there are several actions at which the maximum is achieved, then in the stochastic case, we need not select a single action from among them. So instead of selecting a maximizing action, we can be given a portion of the probabilistic of a particular greedy policy to be selected. So this is a certain case in which it is stuck here. This is a stochastic case that we look at here. Which have they easily extended to this guy. So, yeah. Then in the empirical evaluations, we always do this kind of stochastic update every time. And yeah, we since we need to achieve it in a limited time interval, so yeah, some maximal actions that we need to take. The empirical, the second equation that we had. Ah, yeah. So this the I think so. They gave it the empirical expectations that we evaluate on. So yeah. So this is with respect to the tabular methods that we have. And this gives an example of the 4.1 and the policy and the state space that we needed to select it based on the policy improvement. This is an example of maximum they achieve and any approximate the policy of the probabilistic amongst these actions is permitted. Uh, approximate, okay, and yeah, this then we go on to the policy iteration that we looked at just now. It's just a sub way kind of how do I say it? Deterministic uh, uh, dynamic programming point of view, because we are using this in this space too. Then this is the equation. This is the algorithm that we have used here. Any queries up until now, or you guys need to uh, want me to explain something? I'm just kind of going at the high level because we already have read and understand these things. So I'm totally skipping at the nitty-gritty of it. If you guys do not understand anything, uh, would want me to dive deeper into it, yeah, please feel free to interrupt. This is the evaluation and the improvement step. Then this is the Jack Garland tools that we take a look at. Then took a look at. Then there's policy improvement theorems, and these are the examples, exercises. I haven't solved them, but any more queries, or should we delve into the exercises here? Okay, so let's try to quickly go through what is required. The policy iteration algorithm on page 80 has a subtle bug in which may never terminate if it continuously switches between the two or more policies that are equally good. Modify the pseudocode so that the convergence is guaranteed. Page number 80. Okay, here. So here they might old action. They have compared it. So here, I think so.
So here we got to compare the values of action instead of actions to avoid this to avoid infinite loop when we switch between actions. or another approach one can take, as I did like in my implementation. So my policy just outputs the probabilities of actions instead of concrete actions, and then you just compare the change, like difference in action probabilities instead of and obviously when you have two, like under greedy policy, when you have two equiprobable actions which are optimal, the probabilities wouldn't change in any, if you don't have any further improvement in the policy, right?
Yep. But here also we have to introduce a term here. So I was thinking of the mistake will be in having the reward plus the max that we are trying to evaluate. I'm not too sure, but yeah.
Yeah, we can just compare the values of the actions instead of comparing the actions itself. So in that case, if we don't have any better value for an action, we count it as the same policy, or stable policy, instead of keeping trying to like iterate further, because we care in the value improvements, not about the changes in policy. If two actions lead to the same value, then the policy is not improved, and we can count it as stable, right?
But we need some sort of a priority to then in this case, which action. So instead of one step that we are trying to do here, we might have to go a couple of steps then deeper to select the best policy that we have. So in
Well,
in
I don't think so, because of this recursive definition. We don't need to go any steps deeper, because we actually our greedy action is optimal action, or like our in case if we have like optimal values, our greedy action will be, our greedy policy will be optimal policy. So if we compare the values, and if the values kind of converged, then we reached a stable policy.
Yeah, I totally agree. But the specific case that they had was with respect to the actions that that do not make two or more policies that are equally good. So
Yeah, so if those two actions are equally good, then we don't care which action we choose, and we stop at random action, and by comparing the policies, not the actions, right?
yeah, that makes sense. But we can also go to a couple of steps instead of one to actually evaluate the uh, route. So instead of if I try to graphically give a backup here, yeah, since this is in one state, so yeah, we can do it here like this can be extended to this too. So uh, uh, this kind of this can be kind of be like a third in a loop. I don't know if that makes sense in uh, I'm just thinking on the fly here, but
Yeah, that is not necessary, because we like in this particular setting, we
Yeah,
assume that we know our environment, and we can like find like basically we can estimate our value function with like whatever precision we want to have. In case if we have like some model of the environment which is not perfect, that would like looking a couple of steps further would like have some value in it, but not in this simple setting, right?
Yeah. Totally agree. Yeah. Okay, then for the 4.5 is also iterations we define for action values. Yeah, please go ahead.
I think for simple examples, like the one you see in this with the 14 states, this grid world, small grid world, maybe an option will be also to compare the sum of the state values using one policy against the sum of the state values using another policy. And at the end, one of both will give a better
maybe
result.
I can show an example and like kind of like what I've got with simulations here and like coding this stuff up, and maybe that would kind of be helpful because for me it kind of helped to understand. So if you'd like to see, I can share a screen and we can kind of look at the simulations as supplementary material to yeah.
Yep, I will stop my screenshot just a minute. Give me.
Yeah, I think if I go on and share, it will stop your sharing.
Yep, please try that. Okay.
So do you see my screen?
Yeah.
Yeah. So here, yeah, where it starts. So the first like part of it is policy evaluation, and here it is. So basically, what we do here to like re-implement what they have in the book. Yeah, we construct a simple grid world problem and create an agent which we use for like evaluating the value function. So the agent here basically just holds this value function. And so the process itself is we iterate over all states, and we update for each state. We like we take the possible actions. So here I have a like utility function which gets probability for each actions under random policy, and so we take this for each possible action. We compute the value like as a reward plus value of the next state. So and we do that iteratively until our like this delta here is smaller than some threshold. And here this is kind of like reimplementation of the diagrams we saw in the book. And like here you can see after the first iteration we have all negative ones here, and hopefully that makes sense because we started with all zeros here for each value estimate, and we just took a single step for updating each state, and that was just the reward of -1. Next, at the next state, we have kind of better estimate of this value function, and here you can see that there is some difference. There is some difference here, and for the next state, we kind of have this better estimate, and as we go further, our estimates move to the, and yeah, by the way, in the right-hand side, we have this policy, and I don't show all the arrows because it was kind of tricky. I would have to find for those symbols, but I was kind of lazy to do that. Basically, here this arrows just point in random directions if you look at it. But after just a couple of steps, you see that the arrows are pointing in optimal directions already, and that is achieved by updating the Q function behind the scene. But that's not the so essentially what we do if we go to high enough number of steps, we get this value function estimate that is quite close to the exact solution for this problem, right? And we can get this exact solution because we know the environment perfectly. Okay, so does it make sense? And this exact solution, this estimate, it is close enough to exact solution, and basically it is stable, right? And that's policy evaluation. And what we do, for policy iteration, we do this. Okay, so here it is. We do one step of policy evaluation, which is itself iterative process, and then we have policy update, which is again an iterative process, and that is done by assigning the action, by computing the action values and choosing the best action value, action that grants the highest value, and so that's a greedy approach, right? We just set new action to be yeah, I do it in probabilistically, so the probability would be assigned equally to those actions which maximize our value action values, this action values for each action. So that would be Q of the like it's defined in the book, right? And here you can see that after just single iteration, basically we done for this simple problem, we done one step of policy evaluation and one step of policy update. So and this already gives you an optimal policy. And yeah, so I can, or no, I can just show the values which are associated with this policy, and you will see that those values are already stable values. Whatever. So here you see that we have -3 for this state, -2 for this state, and -1 for this state, and that's optimal value. You cannot do better under this kind of conditions we have, right? And so coming back to our problem, basically in this state, whatever we do over this over what is already done, we cannot improve it further. Okay, it makes sense. So summing all the values and evaluating that wouldn't make sense, because that like optimal policy would yield the same sum. And looking forward, like looking couple steps forward, also wouldn't improve this, because it's already optimal, and that is achieved because we have this perfect knowledge of the environment. So the estimates we get here, those estimates are actually solutions for our problem. Those are not like approximate solutions. Those are like really solutions. So yeah, so that's why we cannot improve it further by like break the ties by doing any extra tricks, because those extra tricks do not give us any extra information, because we already got the optimal policy and optimal value function associated with that policy. So yeah, so I don't know, like, does it make sense to you, and do you agree with this, or maybe we can discuss it further if you have some like counter points to that? Because that's kind of my interpretation, and obviously, yeah, so someone can know better, for sure.
I think in this case, yes, once you reach optimality, then you cannot improve any further.
Yeah, so basically for these states here, we do not care if we go this way or this way, and we like we reached optimality, and like whatever we do, like we cannot like do something to choose between these two actions, because these two actions are actually equivalent. Like we really do not care what we do when we are in this state, because it gives us the same value. But if we would have like this imperfect model of our world, I guess in that case, there are like a lot of ways to do something to get a better policy, like looking forward more steps than one, or something like that. But I guess that those are a topic for further chapters, right?
Yep, totally agree. This is a kind of a deterministic value iteration that we have done. The MDPs here are totally in a end-to-end dynamic environment. So uh, uh, it's the convergence. I think the reaches in less than 10 steps. Uh, if I'm not mistaken, R2 here.
As a convergence, like basically, like to converge to optimal, like really estimate the optimal value functions as they have it. Like here, you can see that it's kind of approaching to it, but the value function like is estimated exactly like in the limit, right, to
Okay.
infinity. But the policy doesn't change after just like I don't know, 5 or 4 steps. We already, okay, so at 3 steps we have this pointing in that direction, which is suboptimal, I guess. But in the first step, already all the policy is optimal. So here you see it just, yeah, so that's not very helpful that I don't have this multiple arrows in the cases when we don't care, like when we have two optimal choices. But basically, if you follow each arrow, you will like follow the optimal trajectory. Yeah, and another like interesting thing, and that's mentioned in a book, that we basically can get faster convergence if we instead of doing this having this two arrays for value, we can have like update it on the fly. And yeah, as you saw after the first step in the previous case, we have this negative ones everywhere. But if we change to like using the values when they are ready, you see that this becomes like asymmetric because we for these later steps we already are using those estimates like we computed. But again, it will become symmetric after some steps, and it converges to optimal values faster. Yeah, so here like negative 22 is the exact solution, and here you see negative 1.99. So that's and we get it, I don't know, maybe at step 50 it's not perfect yet, but at step 100 we are basically very close to the optimal values, exact values. Yeah. Yeah, so that's short demo. And I think we can get back to the book.
Yep.
Thank you. It was a nice implementation. And going back to the exercise, I think you're right. We should compare the value of the action and not only if the action is different, right?
Yeah, even though that actions might be different, the value like is the same, or like to make it like to account for some numerical instabilities, we can just like make some epsilon and compare those with like if those are within certain threshold, to avoid the case when we like really have some numerical issues coming from the computation. Yes. So we discussed 4.4, right?
So, yep, we discussed 4.4.
Now for 4.5, give complete algorithm for computing Q star. Yeah, I guess that's like pretty similar, but instead of updating the value, we just update Q, which would contain a value for each action. And yeah, so I had that in my implementation, and that was basically one line of code added. And like it's basically just mostly the same, but you got to hold a value for each action associated with each action instead of holding a single value for a state.
Totally agree. Yeah. Then the 4.6, we have the considering the policies that are epsilon soft, meaning that the probabilistic is at least epsilon by the norm of the states, the action value of the states. Uh, uh, and this was required for step 3, 2, and 1. This is the policy iteration algorithm V star on page 80. What they have done is instead of a simple max calculation, we will use this formulation here. So uh,
Yeah,
mm,
I guess I just so what I did was just working with this thing from the start, because like that was just came to my mind intuitively at first. You just need to in like in probably in the book formulation for this algorithm. Maybe we can go to the algorithm in book for that.
yeah, on page 80.
Yep. So here they what they do, they update
This
update
is
this values, looking at their like by taking an action uh, under policy, right? But if we have epsilon greedy policy, we can take each action with some non-zero probability. So we would have to sum by like over the this expected returns for each state, some weighted by the probabilities of the actions.
yeah,
So
yeah.
we would have this extra term here, which goes over like over policy, sums over policy. Right. And for update, basically, yeah. So our policy will not take the argmax, but it will like take a combination of argmax, well, like this maximizing values plus epsilon multiply like epsilon divided by number of actions multiplied by the like expected return. So here we will have another term, right?
Yep, I am not too sure, but yep. The formulation looks and feels like optimal. So, and 3, 2, 1. Here they are referring to the changes in the quantitatively. Co- mm, uh, Other than changing it, I think so. They also want it in an iterative fashion too. I mean, uh, what will be the actual value? Yeah, qualitatively. Yeah, I don't know.
I think they just mean that we don't need to give the exact like to write up the algorithm, just describe it in like the general idea qualitative. How would it change qualitatively? And
Yep.
like qualitatively, it that I guess what I was trying to do.
Yep. 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 Yeah, totally agree. I think so. I was thinking about each and every step, the iteration for example, if I have the random
As to Zarmayank, we cannot hear you. Okay, it looks like Mayank encountered some problems with Zoom, right? Oh, nice.
Yep. Sorry, I dropped off.
Okay.
Mm, then the exercise 4.7, they resolve the Jack car problem with uh, additional car. This is a specific example in which the uh, uh, employee is rides a bus home each night and lives near the second location. They are happy to shuttle one car to the second location for free. This additional car will still cost $2. This is a formulation. Jack has a limited parking space at each location. And if more than 10 cars are kept overnight at a location, then additional cost of $4 will be incurred to a second parking lot. And yeah, so these conditions, on the basis of these conditions, a real problem cannot easily be handled by the optimization method other than dynamic programming. Okay. So I think so. These are kind of a handcrafted conditions that we need to fix uh, in our loop, the second value iteration loop. We need to solve it basis on this condition. So, what do you guys say? In for the exercise 4.7.
I guess we got to like code it up to make like basically it says this is a programming exercise, and so we got to implement this, and I kind of started on it, but I haven't yet finished this rental car scene. Yeah, so I think like I will have it by the next session, and we have 2 sessions planned for this chapter, right?
Yeah. That's why, because this kind of nitty-gritty is essential to going through the specifics of the value and the policy iterations that we are trying to discuss. Yeah, this kind of code example is what I was looking forward to. Next time we will go through the slides and start from section 4.4 to the end, and we will look at the couple of coding examples. Yeah, that will make sense, I suppose.
Yeah, sounds good.
And yeah, and the issues that we have, we will also try to get through it with respect to the uh, uh, initial queries that I think we had some confusion over. So along with that, yeah, that's all from our side. Thanks, and have a good day.
Yeah, thanks, Mayank. See you.
Thank you.
See you.
See you next week.
Thank you, guys.